Hi, this is Stuart, and today we're going to talk about Pivotal Cloud Foundry and 12-factor apps. For those who haven't had a chance to visit 12factor.net and read the factors, here they are. 12factor.net is a collection of the attributes or processes or factors that make an enterprise application, particularly a cloud application, have the desired characteristics of being robust and scalable and so on. This is not an exhaustive list, but enterprise applications, especially cloud applications that don't meet the cloud factor criteria, are probably going to have problems. Number one, Codebase. One Codebase, tracked in revision control, many deploys. Pivotal Cloud Foundry doesn't have an explicit source control system, but it does work better if the source control systems that you use are used effectively. At Magenic, we very much like Git for most of our projects, especially for Cloud Foundry projects, because Git source control has the ability to work in ways that are conducive to delivering enterprise cloud apps into production. Use feature branches to isolate in-flight changes. One of the strengths of Git is how quickly developers can spin up a branch off of the development branch or whatever the working branch is and get into a pattern of doing that, going through a cycle of coding a little, testing a little, committing it to that branch. And then at the end of that cycle, when they think that they have code that is worthy to join the mainstream, doing a pull request so that others can look at the code that they have done, do a code review, and agree that it's ready to join the main branch. And then in a perfect universe, you have a build engine like VSTS or Jenkins that will then detect that the changes happen, something called continuous integration, and do a build over there to avoid the works on my machine syndrome, and take the output of that build and propagate it through the environment. Git also supports the use of tags, which is an incredibly useful facility that you can use to know positively at what point in the source code did a particular deployment come from. So as part of a good build and continuous integration cycle, we strongly recommend that you add one or more tags to the resulting outputs that are then deployed and tested as part of the CD/CT pipeline. One of the things that's a bad smell that we're going to talk about a lot is per environment builds. If your code has to be built for dev and you can't just push that code into the downstream environments like QA, UAT, and so on, that's a bad smell. And we'll talk about ways that that shows its head as we go through the 12 factors. But if your team looks at the code you're developing and deploying, and you can't take the output that comes out of the build and deploy it to any environment and have it work in the desired way, that's a really bad sign. Dependencies. Explicitly declare and isolate dependencies. Another code smell is cohesion and tight coupling. And generally speaking, they're not just an implementation problem, they typically speak to poor architecture and design choices. So a couple of ways of making sure that dependencies are implemented in reasonable ways is to get everybody up to speed on the SOLID principles. If you haven't heard of SOLID before, go Google it and go to the Wikipedia page or whatever and read all about it. But SOLID is one of the pattern sets that cuts across all of the code that you could write in all scenarios. If you follow SOLID principles, you'll have solid code. One of the things that's useful then is to have tools that calculate statistics about your code or do what's called static code analysis and look for code smells. Generically, These things are often called linters or code quality analyst tools or static analysis tools. And many of them produce KPIs or metrics that tell development teams about issues like coupling and cohesion. Implicit dependencies make brittle deployments. And so sort of the rule of thumb when it comes to any kind of dependency that is at compile or build time is that those things should be explicit. And the great thing about most modern programming languages is that they have a package manager. So .NET and Node and Python and Ruby and almost everything except Java has a package manager. And part of the job of a package manager is to manage and make explicit dependencies between components at build time. The other good pattern for making sure that there's fairly loose coupling is to use contract-driven development. In other words, when one component talks to another component, it does so via some sort of contract, and that facilitates the ability to do inversion of control. In other words, when you new up an object, if you're using an object-oriented language, that you pass it everything that it needs. Even client-side frameworks, like Angular, use IOC and contract-driven practices to produce loosely coupled, low-cohesion systems that are easy to maintain and test. Configuration. Store configuration in the environment. So in a traditional, for example, .NET app, the app config and web config artifacts hold a lot of environmental configuration. And over the years, there's been a lot of different approaches to dealing with that, ranging from configuration transforms to swapping out which configuration file is used on a build. But fundamentally, that's solving the right problem in the wrong way. Truly externalizing configuration means that when your code is starting up at runtime, it asks the environment, where is my configuration, and then goes and gets it. And PCF offers two solid built-in mechanisms for that. One is configuration server, which is definitely the AA answer whenever you can do it. And the fallback to that is to use user-provided services. And we have on the same YouTube channel a bunch of videos about using UPSs or some other central configuration library. The bottom line is, when I go from dev to QA, QA to perf, or perf to UAT, or UAT to prepod, and so on, my code shouldn't change. That on startup, we acquire the code. So if you find yourself doing builds per environment, that's a big bad smell. Very few things about modern architecture are as transformative as this idea of externalizing configuration, because it then opens the doors to having configuration used by more than one app or deployable unit to be the same. So things like database connection strings and endpoints to web services and all the other pieces of metadata that might vary by environment. If in configuration all of the modules in a particular environment share the same configuration, you never have the very real and very horrible train wreck of different modules in the same environment having different configuration for the same configuration item. Few things are more important when you're making an application enterprise ready or cloud ready or PCF ready than this central idea of having configuration live in the environment and not be part of the build. Backing services. Treat backing services as attached resources. So what does that mean? Well, first of all, what is a backing service? Things that don't run in PCF necessarily could be backing services. So these could be databases, enterprise queues, enterprise storage, services that are external, integration points, anything that's not necessarily running in PCF. So the way that our apps should know about those is through externalizing the configuration and acquiring them. And the great thing about Cloud Foundry's binding mechanism is that in that binding process, Cloud Foundry does the fix-ups that tell your app code on startup where its configuration is and how to get to these backing services. By the way, it's a best practice to make sure that your apps, the consumers of configuration and services, check to see whether or not A, they actually got the required configuration for them and it looks valid, and B, that they make an early attempt to try to connect to the service. What this means is that a well-designed backing service will have some mechanism of validating that using the provided configuration, I can connect to it and do something useful if trivial. For example, connecting to a SQL database, you might check to see if a certain table exists. That's a fairly cheap query that you can do on startup to validate your connection information. Other types of backing services will have other mechanisms. So if you have SOAP or REST services and they expose a health check endpoint or a version endpoint, invoking that endpoint is a nice way of knowing very early on in the app's startup lifecycle that configuration is correct and that connection is healthy. Build, release, run. We said this before. Don't build per environment. Separate build and run stages. And what that means is having your build produce outputs that are packages, whether that's a folder of files, a zip, a tar, a tarball, whatever the native platform thing is. For .NET apps, zip files are a great way to push things to Windows and Linux stem cells. Tarballs are used for other languages like Go and PHP, and of course jars are used for Java and so on. But the idea is that storage, that package, that collection of stuff is immutable once it's made and is the unit of deployment along with some deployment information that goes from environment to environment. And if you can't do that, it's probably a bad smell. By the way, propagation also has the benefit that we can capture that package and snapshot it for compliance purposes, and we can trace its lineage because in source control we applied tags to our builds and releases so that we have an end-to-end association. And at runtime, if we have a way to interrogate the package metadata, we're able to trace running code all the way back through the deployment pipeline, backwards through the build pipeline, and backwards at a moment of time in source control. And this is invaluable for compliance scenarios. And even if you don't have a driven explicit compliance need, it's great for stakeholder peace of mind. As a developer and an architect, the ability to know that this version running over there can be recapitulated at will by grabbing something at a tag and then running it through the same build pipeline and then looking at the results is hugely helpful for problem solving and so on. Processes. Execute the app as one or more stateless processes. What do we mean by stateless? Well, there's two big use cases in Pivotal Cloud Foundry. One is websites and web services that are expected to be stateless and load balanceable. In other words, if I do a request at a web service and then I do another request at a web service, I shouldn't care if I end up through the load balancer on a different instance. For headless processes like tasks and headless services, what I'm looking for is that they adopt a unit of work pattern in such a way that if the instances come and go, they can start up again. So typically, if we have to have a shared notion of state, really it falls into a couple of different high-level buckets. Work in progress and cache state, which is often usefully satisfied by something like Redis, which is very high performance, or scale out server or whatever. Redis, by the way, is natively available in almost every PCF deployment and is the default go-to. And in fact, you can use Redis sets and ordered sets like cheap queues as well. Longer term state, of course, belongs in an enterprise queue, an enterprise storage, a high availability version of SQL or NoSQL databases, and so on, right? Where the state is inspectable outside of the running process cluster. That's what we mean by long-term state. Port binding. Export services via port binding is the rule. So in PCF, like a lot of other container systems, the container runtime, in this case the Diego cell, tells the application via an environment variable what port or ports it should respond on. And then PCF deals with the wiring up of the externally facing port to the internal port. Kubernetes does the same thing. If you've ever deployed something in Kubernetes with the -p flag and you've mapped one port onto another, that's port binding. By the way, the motivation for using port binding systems is to avoid ugly sharing mechanisms like shared files, pipes, and things that aren't really very cloud friendly. And that may not be properly durable. And in fact, core to the idea of moving to a containerized universe is this idea of process isolation by not allowing shared memory behavior between containers. So port binding, in other words, leveraging the TCP/IP protocol to do all of our interoperations between various components in our system, is by far and away the best practice with very few exceptions. And if you think about the interactions with back-end systems, SQL, NoSQL, storage, web services, and so on, they're all basically leveraging communication over some version of TCP/IP and occasionally UDP. Concurrency. In a perfect universe, I should be able to look at any of the apps in my app and using something like the CFTop plugin or the metrics dot on your API instance, observe that I need to scale that component up, and I should be able to go and say CF scale -I for the number of instances, app name, or go through the UI or whatever, and be able to scale that component up, and it should just work. And if it doesn't work, that's a hugely bad smell. Generally speaking, almost no exceptions, the behavior you want to see is that users and processing is never affected by scaling up, that is, increasing the number of instances. But it may be impacted by scaling down. For websites and web services, typically the Go router is pretty well behaved as things scale down, in the sense that it will stop accepting new requests, but it will allow any in-flight requests to finish. A word of warning about that isn't forever for infinity, right? So there is a time sensitivity to that. And so developers should probably not count on that behavior and instead make sure that their apps are very snappy about being destroyed and being rebuilt and having that be okay. Disposability is that you have container instances that run, and they should start fast and they should gracefully shut down. Now, in PCF, containers can cease to exist at any time, and depending on your app stack, right, and the type of Diego cell you're using, your app may or may not see a SIG-kill signal, or its moral equivalent, that says, hey, this is shutting down, I want you to do something graceful. Again, developers should probably not count on that behavior, and instead assume that their running process can be terminated at any part of the unit of work, and that two things should be true. One is we should never lose our place or what we were doing. And the second is we should be able to resume from that place. And there are lots of good architectural patterns for that. If you have an enterprise queue and your process is dequeuing items and processing them. If your queue implements leasing and your container instance is killed mid-processing, then the message that we were working on will show back up when the lease expires if we don't tell it we've successfully processed the message. That's a nice durability mechanism. Likewise, Saga-type processing patterns look at the state of where a long series of workflow steps are, and they attempt to find where we left off, and then, if necessary, back up until the state is sane again, and then go forward again. Fast fail callee behavior is pretty important, right? If you're exposing a service endpoint like a web service, and it's not going to work for whatever reason, the backend data store is not available, they sent a bad datagram, the request is invalid, they have bad security credentials, whatever, the expectation is fast fail, that we will get a no message back to the caller as quickly as we can. Sometimes called, if it's going to die, let it be quick. The complementary pattern to that is callers should consider implementing a circuit breaker pattern like Hystrix so that the caller can fall back to some set of rules about what to do when the callee returns a less than happy result or is just not available at all. And lastly, for cloud architectures, few things are better than unit of work patterns. Unit of work patterns strung together end to end are what Saga systems are made out of. Each step in a Saga system is a unit of work where the unit of work is triggered by the datagrams being in a particular state or on receipt of a message or an event, and they end with the state and data being updated successfully, or they fail, either gracefully or gracelessly, and that piece of work to do will be picked up by the next unit of work that calls it. In other words, a well-organized system is both lossless and gracefully able to recover. And that's super important because, again, in PCF and other container systems, and even in the real world, if you were writing things and deploying them straight onto the server, you know, those application runtime environments can cease to exist abruptly. And we want systems that are extremely durable and robust. And so planning for disposability is a very important part of writing enterprise and cloud applications in such a way that they meet the 12-factor pattern. Dev and prod parity. I can't tell you the number of times I've been on projects and we deploy things to dev, we do testing in dev, and by dev I mean dev, QA, any of the lower environments, and it's fine. And then we go to deploy it to pre-prod or prod, and it's unfine. So parity is super important. And in PCF, parity has a very specific definition. And that is that in PCF, parity has a very specific meaning. It means that the versions of all of the backplane elements for all of the PCF instances, depending on how you dice and slice environments into instance collections, are of the same version on the same hardware. And that's true also for any Diego cells. And what changes between dev and prod is the numeracy of how redundant is the backplane, how many Diego cells of each kind are available in each environment. But their versions and hardware and operating systems and everything else should be identical. Another area of parity that's super important is that all of the surrounding facilities that PCF offers, from things in the marketplace to logging and metrics and administrative interfaces and things, should be the same across all environments. Now, who has access to those things and what they're allowed to provision or log onto or view or whatever will change, but their versions and their existential nature are the same across all instances of PCF. Logs. Treat logs as event streams. Okay, PCF is all over this like paint because their logging system and the adapters, the nozzles and log aggregation behavior are baked into PCF's infrastructure. And you can read more about that on the link below. What's important, though, is that PCF will collate the logs across all the different layers of a Pivotal Cloud Foundry instance, but those log entries are ephemeral if nobody is consuming them. So the thing that's important is that teams should make sure that there's something collecting the logs, Splunk, Papertrail, Datadog, whatever, so that those log entries aren't lost. And again, parity. Log collection and analysis tools should be done on all environments, and the stakeholders that have access to the environments should have access to the log analysis portal or tool or whatever. Administrative process, otherwise known as tasks and jobs. In PCF, the task mechanism is pretty elegant, and for one-off things, that works pretty well. One of the malformations in an organization that we see a lot is that organizations try to do their application hosting kind of in one place, in one way, and then they have a completely different set of tooling to do the regular administrative tasks that apply to the applications they're hosting. And this is, generally speaking, a bad thing. One of the things that we teach architects early on is the aphorism, the person with one watch knows what time it is, someone with two is never sure. In other words, doing the same things in the same ways, like for like, is a good thing. By the way, on Linux Diego cells, cron is a great way to schedule repetitive tasks. And on Windows stem cells, you can write code that leverages libraries like Quartz.net as a way of doing retrospective or repetitive jobs. PCF is tool factor ready. Are your apps?